Mixture Gaussian model. We already learned about Gaussian distributions. And why did we learn about Gaussian distribution? The main reason was that Gaussian distribution can be used to model natural phenomena or real world data sets. So if you take any data set that is coming out of natural phenomena, or you take any real world data set, we said that you can make approximation using a Gaussian distribution, or you can depict any real world data set easily using a Gaussian distribution. Is that statement actually right? Did you ever give a thought about it? Because see, this is how a Gaussian looks. It looks like a bell curve. Will all the real world data set be so clean so as to depict using a bell curve? It won't be, right? If you take some random data set, some random real world data set, it may look something like this. You won't be able to easily depict it using a Gaussian model. But this is where mixture Gaussian model comes into rescue. That is, if you take any real world data set, you would ideally be able to depict it if it is a mixture Gaussian model. And what is mixture Gaussian model? Let us understand using an example. So I'll rub this off. Let us take an example, because from example and from pictorial representation, a graphical representation, it is easier to understand about mixture Gaussian models. Let us take one data. Let us say this is my graph, and my data, let us say it looks something like this. This is what my data looks like, okay? This is what my data looks like. In this case, if this is the case, if I use a single Gaussian distribution, how will my graph look like? Maybe if I want to approximate this using a Gaussian, I may draw something of this kind, something like this. This is the best I can do. If I can only draw one single Gaussian, this is the best I can do. Let us say the name of the Gaussian that I drew is Q. Q is the distribution, the blue distribution, using which I'm trying to model P, which is yellow. Let me write P the my yellow line, yellow graph. It represents P. So P is my actual data coming from a real world data set. This P I'm trying to approximate using a Gaussian. But because this Q is a single Gaussian distribution, I'm not able to get a clear approximation of P. You can see that at many points, the value given by Q and value given by P are way different. So Q is not the right approximation of P. So how can you approximate P? This is by using mixture Gaussian. As the name suggests, you are going to use a mixture of multiple Gaussian distributions. For example, see, this is why I told I'll show this pictorially, because when I draw this graph, it is easier to understand how I can approximate P using multiple Gaussian distributions. Let us say I'm using one distribution as this. This is my first distribution. This is my first distribution that I'm using. I'll call this as, let us say R1. R1 is my red distribution, okay? And I have a second distribution which I'll draw with, let us say this blue color, light blue. I'll draw a second distribution. Let us say it is something like this. This is my second distribution. Oh, let me draw it again because I lost that red distribution there. This is my actual distribution. Okay, it looks, let's say something like this. This is my actual distribution. So when I try to let me write P here. When I tried to approximate P using another Gaussian distribution, it looked something like this. This is what it looked when I tried to approximate P using a Gaussian, and I called it Q. And the third time I'm attempting using mixture Gaussians. So in the mixture, I can have multiple Gaussian distributions. So the first one is this, which I call as R1 is my red distribution. Then I'll use this light bluish green. So this is what I'll use for the second Gaussian in my mixture, which is maybe something like this. Okay, this I'll call as R2, and I'll have a third distribution. Let's say I'll use gray. Using gray, I'm having a third Gaussian distribution. It is something like this. Okay, this is R3. If you see this now, the situation is that using R1, R2 and R3, that is a mixture of all these three, I can quite closely approximate the actual distribution P, because the leftmost part of P is very well approximated using R1. The middle part of P is very well approximated using R2, and the rightmost part of P is very well approximated using R3. So using a mixture of these three distributions, R1, R2 and R3, I am able to come up with a very good approximation for the underlying distribution, which is P. Instead, if I used a single Gaussian, that is Q, this is the best I can come up with. This blue line is the best I can come up with in case of a single Gaussian distribution. But if I'm using a mixture Gaussian, then if I use R1, R2 and R3 together, in this case, I'll be able to come up with a good approximation for the distribution P. So I'll write the equation, and from that let us understand. Okay. For Gaussian model, this is how the equation looks like. Normally you write a Gaussian distribution like this: n of x given mu and sigma square. Coming to a Gaussian model, this sigma square is the variance. Instead of variance, you sometimes use the covariance matrix, that is sigma. Sigma denotes the covariance. So covariance matrix is used in place of variance, and using variance, that is covariance, and mean as the parameters, you will be able to approximate it using a Gaussian distribution. So n of x given mu and sigma, this is your Gaussian distribution. In case of mixture Gaussian, what you do is you superimpose multiple Gaussians. Let us say you have k different Gaussians. Your final probability density function p of x, it will look something like this. It will be summation over all the values of k. Let's say k is equal to 1 to k. These are the values of k. Pi k, we'll explain what is pi k. Pi k into normal distribution or the Gaussian distribution of x given mu k and sigma k. So this sigma is of covariance matrix, and the first sigma that I wrote, this is of summation. Okay, these are totally two different sigmas. These are not related at all. So you have k different Gaussian distributions which you are using in order to approximate some real world distribution. Let's say I'm rubbing this off. So my probability density function would look like this. It is a summation of various Gaussian distributions which are taken in proportion of pi. So pi tells you, pi is a coefficient. This coefficient tells you what is the importance of each Gaussian distribution in this final distribution. What percentage or what fraction is the importance of each Gaussian distribution that you are using in this mixture. That is what pi will tell you. So this is how you want to understand that by using a sufficient number of Gaussians and by adjusting the mean, covariance and the coefficient, you will be able to almost any continuous density you will be able to approximate using this mixture Gaussians. So this is what you have to understand as a final point. That is, if you have k different Gaussians, then by adjusting the mean, mu k is the mean of the kth Gaussian distribution. If you are having k different distributions, each distribution will have their own mu and sigma. Sigma is the covariance and mu is the mean. Each different Gaussian distribution will have its own mean and covariance. So considering mu k as the mean of the kth distribution, kth Gaussian distribution, and sigma k as the covariance matrix of the kth Gaussian distribution, and pi k as the coefficient. This coefficient tells you what is the weightage of this particular Gaussian distribution in your total mixture Gaussian. If these three values are adjusted perfectly, then any particular continuous density can be approximated using a mixed Gaussian model. So this is the point that you need to understand. And the conditions here, first condition is that summation over all k pi k, this should always be equal to 1. That is, if you take k equal to 1 to k and you do the summation, pi k should be equal to 1. This means each value of pi k would be something like this: 0.1, 0.3, 0.2, so on. This will tell how much is the importance of the kth Gaussian distribution in the total mix. If you have 3 or 4 different Gaussians in the mix, then what is the weightage given to this particular kth Gaussian, that is given by pi k. And the other conditions, those are similar for any particular probability that you take. First thing is your p of x, it should always be greater than or equal to 0. Probability can never go negative. So your probability density function, it should always give a positive value. And the second thing is that if you take any Gaussian, the Gaussian should always be positive. N of x given mu sigma, this should always be positive. Each of the component Gaussians, see, by default all the Gaussian values will be positive. And the other thing is pi k, the coefficient, that should always be positive. So under these conditions, if you use this formula and calculate the mixed Gaussian, you should be able to approximate any of the real world data set or any data set coming out of natural phenomena. You should be able to approximate using a mixture Gaussian, which says the probability density function p of x is equal to summation over all the values of k pi k into Gaussian. That is the component Gaussian. Each of these are called component Gaussian. N of x given mu k sigma k, where this mu k is the mean of the kth Gaussian distribution and sigma k is the covariance of the kth Gaussian distribution.